Everyone, welcome back to my YouTube channel. I'm Ananya, currently pursuing my bachelor's degree in Sri Venkateshwara College of Engineering in the Department of Computer Science and Cybersecurity. Today, I'm here with the topic from Theory of Computation, that is non-deterministic finite automata. So what is an NFA? It's a computational model that can be used to recognize patterns in strings. It's like a machine that can read a string of characters and decide whether it matches a certain pattern or not. So, what are the key components of an NFA? Well, there are five main parts: states, input symbols, transition functions, a start state, and accept state. Think of states like different modes that the machine can be in. Input symbols are the characters that the machine reads. Transition functions define how the machine moves from one state to another state based on the input symbol. The start state is where the machine begins, and accept state are where the machine ends if it recognizes a string. Now let's talk about the transition functions in more detail. In an NFA, transition functions can map a state and input symbol to a set of possible next states. This means that the machine can move to multiple states at the same time, which makes it non-deterministic. The machine can also transition without consuming the input, which is called as epsilon transition. So how does an NFA decide whether to accept a string or not? Well, the machine accepts a string if there exists at least one path through the machine that leads to an accept state. It's like finding a treasure map. If there at least one path that leads to the treasure, the machine accepts the string. Now you might be wondering how NFAs differ from deterministic finite automata or DFAs. The main difference is that DFAs have exactly one transition for each input symbol from a given state, whereas NFAs can have multiple transitions. Despite these differences, NFAs and DFAs are equivalent in terms of the language they can recognize. Epsilon transition. Epsilon transition allow the machine to change states without consuming any input symbols. This feature enables the machine to explore multiple computational paths simultaneously. We construct an NFA. We can construct using state diagrams to visually represent states and transitions. Each state in the diagram corresponds to a node, while transitions are represented as directed edges. NFAs have many practical applications such as lexical analysis in compilers, pattern matching in text processing, and designing efficient network protocols. Despite their many applications, NFAs do have some limitations. For example, they can be less efficient in terms of memory usage compared to DFAs. Additionally, the non-deterministic nature of NFAs can lead to complexities in implementation. In conclusion, non-deterministic finite automata are a powerful concept in the theory of computation. With many practical applications, understanding NFAs is essential for grasping more complex computational theories and algorithms. Thank you for your attention.